So we are almost nearing our end to this lecture series, and currently we have done so far was the Lagrange. We took many prerequisites so that we can define an equation for Lagrange's equation of motion, and we saw about the kinetic energy in generalized coordinates. Now we are going to see what's called as a cyclic or variable coordinates. What it means by having this kind of simplification. So how this kind of simplification will help us to further review our topics, so we can see how we are going to express our expressions rather than getting into a vicious cycle of remaining inside an equation. So let's seek some help. Just a second. So now we are going to describe. So recall that the Lagrangian is written as a function. Normally, Lagrangian is written as a function of generalized coordinates, generalized velocity, and time. Right? So if I say, let's say time is important, it remains there. So I only consider, say, Lagrangian is q, depends on q and q dot. Of course it depends on time, but for our discussion, let's say it depends on q and q dot, because q and q dot have unique representation, while t has a unique representation. Q and q dot have unique representations for, say, q1, q2, dot 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 dot. Similarly, q dot 1, q dot 2, dot 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 dot. While t is just t. So that's the reason I'm just taking this for our current discussion. So if say I'm just going to tell you further ado that I haven't prepared notes for this particular topic, and you won't even require it if you just if you just focus on the lecture. So I hope you can take a screenshot, or you can take notes only for this particular series. This particular topic. So the Lagrangian is written, say, as a function of q and q dot. Where q is my qj and q dot is my q dot j, where j runs from 1 to n. If any one of the coordinates, let me expand this. q1, q2, dot 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 dot, q k minus 1, dot 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 dot, qk plus 1, dot 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 dot, qn, and then we have q dot 1, q dot 2, dot dot dot, we have q dot k, dot 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 dot, and q dot n. So my Lagrangian depends upon this following variables. Alright, it has qk minus 1, it doesn't qk plus 1, but it does not have q of k. So I say if any one of the coordinate, the generalized coordinate of course, say qk is absent in the expression of Lagrangian, then my partial derivative of the Lagrangian n with respect to qk will vanish. That means mathematically this could be my case, right? So if any one of the coordinates, as I took here qk to be the case, is absent in the expression of the Lagrangian L, the partial derivative of L with respect to qk will vanish. Thus, the equation of motion corresponding to this particular variable qk becomes d by dt equation of q dot k minus dou L by dou qk is equal to 0, where we use the Lagrange's equation of motion. But we know this is 0, so this particular term is 0. That implies this particular term vanishes and this particular term is equal to 0. So if anything, if a derivative is if a derivative of this particular value is equal to 0, this means this particular quantity must be a constant. And it is evident that whenever a term constant comes into picture in mechanics, it means the corresponding quantity is conserved. Is constant. Now, this particular quantity is defined. Is called, this particular quantity is given its notation as q pk, which is equal to dou L by dou q dot k, and this is equal to constant. Now this particular pk, this particular quantity represents what's called as generalized momentum, or we call it as canonical momentum. Let me write it down, or even the conjugate momentum. So this quantity pk is called as the canonical or conjugate momentum. So what happens is this particular momentum, this particular canonical momentum is conserved. So thus, whenever my coordinate, say qk, does not appear explicitly in the Lagrange's function as it happened here, it's not visible. Like, it's visible to us that it does not appear explicitly, right? As a result of which, explicitly in the Lagrangian function corresponding to the linear momentum pk is a conserved quantity. See, it's a conserved quantity. It's a constant of motion. Now such a coordinate such a coordinate such a coordinate qk is called as cyclic or ignorable coordinate. Now, what happens is so if you see, this is my equation. This is my equation. So I defined a Lagrangian, and it depends upon the following function. I say the qk does not appear explicitly in the Lagrangian. That means my dou L by dou qk equal to 0. Thus, I use the Lagrange equation of motion, and I find this quantity to be equal to 0, and I find d by dt is equal to this particular value, this particular parenthesis is equal to 0. If anything, if a derivative of a particular variable is equal to 0, that means that variable must be constant. As a result, we get dou L by dou q dot k is equal to constant. That means I define this quantity to be pk, which is later called to be canonical conjugate momentum, or generalized momentum, and this particular term appears to be constant because of this explicit result. As a result, we say such a coordinate qk is called a cyclic or ignorable coordinates. So now, if you, I'm not going to go into details. I'm going to state this. There should be a deeper relationship between what's called as cyclic coordinates and the physical nature of motion of the system. When a generalized translation coordinate, say qk, is cyclic, that is absent in the Lagrangian function as we just saw from the definition, it means that the system can be translated along the direction or along qk without any effect. Without any effect on the Lagrangian. That's amazing. That's an amazing result. See, the Lagrangian function is unchanged under this translation, and the equation of motions remains the same. We say that the system is invariant under translation, or the system is said to have a translation symmetry. This is where the symmetry comes into picture. I'm not going to go into the depths because it is very beautiful phenomena, but it requires quite a lot of advanced mathematics and quite a lot of physical as well as the classical mechanical understanding. There are research papers on these topics also. Now this immediately leads us to the what's called as the conservation of conjugate momentum. I just stated the result, but there are different ways we obtain this result. This immediately leads us to this particular conservation. This is amazing. So if the rotation, see, what we can do is a similar consideration. By considering similarly, we can say having a rotational symmetry. So translation symmetry was one case, right? And now if we consider the rotational symmetry, so how does the rotational symmetry comes into picture? If the rotation of the system about a particular axis is conserved, it leaves the system unaffected. That means along that axis the system is unchanged. The corresponding coordinate would be a cyclic coordinate, or have a cyclic, and the component of the angular momentum in that direction is conserved. So, what we have seen so far is how the linear momentum and the angular momentum of a system corresponds to the translational symmetry and the rotational symmetry. Let me write it down. The conservation of momentum leads to translational symmetry. Similarly, the conservation of angular momentum leads to what's called as the rotational symmetry. So it appears to us that this approach involving the considerations of symmetries is very fundamental, and it appears to us that the conservation of energy of the system must also correspond to some sort of symmetries of the system. Conservation of energy should also correspond to some sort of symmetry. That's an interesting question, and this symmetry is with respect to the translation of the system, and this symmetry, as it is found that this symmetry is with respect to the translation of the system along time. So I will discuss the conservation of energy in length, because I have to derive an equation about the conservation of energy, and it is one of my favorite topics in application of Lagrangian equation, because conservation of energy just rises my enthusiasm to a whole new level, because conservation of energy is considered to be some sort of fundamental, and I consider it because it's kind of a high value program that you just seeks in a way of getting to the career. Before moving on, I like to present you with an example of cyclic coordinates so that you will get an idea of how to use it. Because the theory isn't much long, the application is what's considered to be important when we consider the examples, when we consider the topics such as ignorable or cyclic coordinates. Okay, I'll just give one example. This example should be very much familiar to you because we are going to consider this example from the central force motion. So since you might all seen about the central force motion, I'm going to consider the same example so that you will have an idea. Suppose you consider the sun and the earth system. So my kinetic energy, if you remember, I told you that please remember that particular kinetic energy equation. Writing this equation, you will remember half m r dot square plus r square theta dot square. Remember, I gave you this as an example in case of the while discussing the kinetic energy. Now, in this case, I'm going to consider m rather using m. I'll rather use mu, which stands for the reduced mass. And this is our acceleration. This is our velocity square term in the plane polar coordinates. And if you remember in central force motion, I said the motion happens only in the plane. This is a consequence of the conservation of angular momentum, and we will see that how this happens. So my kinetic energy is this. My potential energy is given by this particular formula, and my m stands for mass, ms upon r. ms stands for the mass of the sun, and e stands for the mass of the earth. Now, how we define it? We define Lagrangian as t minus p. So we substitute the above equation: earth square plus r square theta dot square, minus becomes plus Gme ms upon r. So this is my Lagrangian. So if you see, my Lagrangian is a function of what? It is a function of r dot. It is a function of r. It is a function of theta dot, but it is not the function of. It is not the function of theta. Function of theta. Can you see anywhere theta appearing? Theta dot is appearing, yes, but theta, no appearance of theta. As a result, my theta becomes a cyclic coordinate. It's a cyclic. So that means my corresponding conjugate momentum is conserved, or it's constant. Right? So since I have theta, I define p of theta. So I use this equation. I use the partial differential of L with respect to theta dot, and I find the following to be conserved. And if you see, this is of the form mr square omega, which is nothing but the angular momentum. Thus, angular momentum is constant as a result in the case of central force motion. This was a beautiful example presented to you with a connection of the previous learning. I hope this really helps you. So that's it for this lecture. So my final lecture would be on the energy conservation, and I'll present you with the problem sets.